Okay, a pleasant afternoon to all of you. Good day, rather. So I hope you are doing good and great for today's session. So our topic for today is all about reflection and stretches. So do you have any idea about how graphs or how functions are being reflected and being stretched? So if you don't have idea, you better watch this video discussion. Okay, let's start. So to start with this topic, of course, we have to be guided with the learning objectives. And we have here the following learning objectives that we have to remember, or so that we should be, or we will be guided rather for today's session. So first, you are expected to focus on developing an understanding of the effects of reflections on the graphs of functions and their related equations. Another thing, developing an understanding of the effects of vertical and horizontal stretches on the graphs of functions and their related equations. So now, I guess you are ready. You can't wait to proceed to the next slide. So, of course, let's try to think about reflection in real life. I believe some of you have experience about reflections. Of course, you can relate to this because this is, or this can be seen in our in our day-to-day living. Okay, so let's have the examples as you can see in the picture. Oh, so nice picture, right? Okay, so another thing, a cat, so cute, right? So we have it here, there, the object and the image. Of course, there is an axis of reflection. So from it, we can have a mirror line. We can draw a mirror line to the shape and also its reflections. You can see there on the screen. So I believe you have the idea already about our main focus for today's session. So yeah, there is a symmetrical balance in it. And reflection, don't you know that reflection, symmetry, as well as horizontal and vertical stretches appear in architecture, textile, science, and of art? When something is symmetrical or stretched in the geometric sense, then its parts have a one-to-one correspondence. So how does this relate to the study of functions? So from geometry, from the basic concept of geometry, we can really experience and feel and appreciate reflections through the images. So we can say that it's more on designs or architecture that we can relate to it. But this time, I want you to think about this one. How will you relate reflections in function? So have you ever experienced it before? So if not, then it's better for you to keep watching this video. So as I have said, I highlighted a while ago. So now let's try to investigate and do the think, solve, share activity. So in this investigate activity, or shall I say think, solve, share activity, you're going to investigate the reflection and stretches of functions. So you have it there, a graph. You're going to graph reflections in the x-axis and the y-axis. So just follow that one. And if you're not part of my class, then you can leave this area, okay? What I mean, you can leave this a slide. So you can just have it and do this investigate part later on in our discussion or in our Google meeting. So let's now proceed to the next slide. So just skip this one. So draw a set of coordinate axes on grid paper in quadrant 1. Plot a point A, labeled point A with its coordinates. So use the x-axis as a mirror line or line of reflection and plot point A prime, then the mirror image of point A in the x-axis. So you can have this. So their y components are opposites of each other. So if you try to do this investigate part or activity, then you will find out in letter C that how are the coordinates of points A and A prime related. So you'll be able to identify that their y components are opposites of each other. So I want you to think about it, and I hope you have the same findings with this answer. Another thing also, if point A is initially located in any of the other quadrants, does the relationship in part C still hold true? Let's try to think about it. So let's see. The answer is yes, actually. And of course, consider the graph of the function y is equal to f of x. As you can see on the graph, you have there the graph of y is equal to f of x. Then explain how you could graph the mirror image of the function in the x-axis. So how do you think? How do you do it? What do you think? Let's see. Okay, find the negative of the y components. Take note, okay, because that will be something related to our topic for today. Find the negative of the y components. So find the negative of y components. When you say y components, the y coordinates or the y values rather for each point, and plot the x component of the value. So I hope you can follow. Okay, you'll experience that one later if you cannot relate to it yet. No worries, don't be disappointed if you couldn't relate to it. So now make a conjecture about how the equation f of x changes to graph the mirror image. Now all the y components or y coordinates or y values take the opposite sign. So the function is multiplied by -1. So I hope you have the same idea while doing this investigate part of our activity part rather in our session. So now let's try to think the idea, link all the ideas that we have there in the investigation part of this activity. So we can link the ideas that reflection, or we can define a reflection formally in this way. A transformation, of course, a transformation where each point of the original graph has an image point resulting from a reflection in a line. So there is a reflection in a line in the reflection or in transforming a function using a reflection. Another thing also that I want you to consider and to link the ideas is about you may result or reflection may result rather in a change of orientation. So when we say change of orientation, the value or the components of your x and y will be changed probably, most probably, of course, especially in your y coordinates, because you're going to multiply -1 as how we did it a while ago. Or you could even have it like multiply -x. Multiply -1 rather to your x component, or you can do the vice versa thing. So of a graph while preserving its shape. Okay, the good thing in here, the shape will not change, only the orientation. So please take note of that. So a reflection of a graph creates a mirror image, of course, in a line which is called the line of reflection. So I want you to consider that one, the line of reflection. So reflections, like translations, do not change the shape. Take note of that. It does not change its shape of the graph. However, unlike translations, reflections may change the orientations of the graph. So they only differ with translation, because in translation, it will never change its orientation, but reflection will do. Why? As I have said a while ago again, you will just multiply. Yeah, it's there on the screen. I'm just being advanced, telling you about it. So later we will all talk about it also after. So now when the output of a function y is equal to f of x is multiplied by -1, so the result y is equal to negative f of x. This is what I said a while ago. So you can just multiply -1 to your f of x. So it will become y is equal to negative f of x. So this is a reflection of the graph in the x-axis. So I hope you can follow, and I hope you can all determine about how will you do the reflection as a transformation in the x-axis. Okay, so I hope you can follow. Another thing also to consider about doing reflection as a transformation of your function. So when the input of a function y is equal to f of x is multiplied by -1, the result will be y is equal to f of -x, which is the reflection in the y-axis. So I want to highlight this concept because this is very helpful, most especially when we do or when we try to combine all the transformations that we have in the function. So please make sure and please remember that when you multiply -1 to the output, it gives you y is equal to negative f of x, as I stated in here, and this means that there is a reflection in the x-axis. So if you are going to multiply -1 to your input, then you can have it in the form of, or the function will be transformed into the form of y is equal to f of -x. And that means there is a reflection in the y-axis. So I want you to remember that one. And of course, let's now proceed to the next slide. Okay, I guess you are still alive in spite of the reflections that we're talking about here. So now let's let's try to apply the example or the concept of reflection in this example. So let's try to compare the graphs of y is equal to f of x, and then y is equal to negative f of x, and y is equal to f of negative x. Okay, I know some of you are very eager to learn for this. So just stay put, and then you can just answer letter A and B. Okay, so I'll give you time, perhaps maybe later. We'll just discuss it if you have some questions about it. So now, if given the graph of y is equal to f of x, graph the functions y is equal to negative f of x and y is equal to f of negative x. And here in letter B, how are the graphs of y is equal to negative f of x and y is equal to f of negative x related to the graph of y is equal to f of x? So as you can see, this is the graph. So I am going to highlight this one. So this is the graph of y is equal to f of x. But if you cannot follow because I'm so fast, you can just turn on or something. You can watch it again, over and over again, okay? Several times. It's unlimited. Okay. So now let's try to answer the example, or let's try to apply and study the example that I presented in the previous slide. So now the solution. Use the key points on the graph of y is equal to f of x, as you can see, to create table of values. So the image points on the graph of y is equal to negative f of x have the same x coordinates, but different y coordinates. So that's it. That's the difference. It changes its y coordinates as part of the rule in the reflection, especially along the x axis or y axis. So in this case, since we have negative f of x, it will be along in the x axis. So if you have remembered about the rule a while ago. So multiply the y coordinates of points on the graph of y is equal to f of x by negative 1. So see what happens. So you have it here. This is your y is equal to negative 3, negative 3, negative 0, 4 until negative 4. So this is what we did to get its reflection along the x-axis. Let me check. Okay, this one, yeah, along the x-axis, you can see. So you have it there, negative 1 times negative 3, it becomes positive 3. So as you can see, the x-axis did not change, only the y-axis, because we followed the form of negative f of x. We just multiplied negative 1 to your y coordinates or y components. That's why your y changes if you wanna get its reflection along the x-axis. So you are going to multiply negative 1 to your y. Okay, please don't forget about it. The negative sign can be interpreted as a change in sign of one of the coordinates. So I hope we're clear about it. Okay, so let's see the graph. Okay, this is now the graph, as you can see there. Oh, I covered the graph. So this is the graph of y is equal to negative f of x. As you can see, we just multiplied negative 1 to your y coordinates, and you can use the symbol prime, the prime symbols, as to represent your the coordinates of your new image points or reflected transformation or image point. So I hope we're clear about this one. So you can have it. So each image point is the same distance from the line of reflection as the corresponding key point. So a line drawn perpendicular, so you can see it's perpendicular. Actually, we can draw a perpendicular line. Look at the x-axis. It's trying to we can find the perpendicular line there to the line of reflection, contains both the key point and its image point. So I hope we are clear about this one. So this is what I said. Look at the x-axis perpendicular to it. It's like the reflection. Of course, you can see that it's really a reflection of the graph. In the graph, y is equal to f of x. Okay, so now let's try to continue for letter B. So in here, we're going to compare the graph of y is equal to f of x to the functions of negative f of x and y is equal to f of negative x. So now use the key points. When we say key points again, you can use table of values if you don't like to use the key points, of course. So the image points on the graph of y is equal to f of negative x, as you can see, have the same y coordinates but different x coordinates. Multiply the x coordinates of points on the graph of y is equal to f of x by negative 1. So what will happen? Okay, let's see what happens. Okay, this is the the graph. As you can see, -4, we just multiply, yeah. -4, of course, for the y, it has -3. Then after it, after this one, we can just multiply -1 to your x coordinates, okay? So we are trying to compare the graph of y is equal to f of -x. Of course, as expected, we're going to multiply -1 to your x coordinates or x components. And that means your x coordinates or x components will be changed and your y will not be changed. Y values rather, or y components will not be changed. As you can see, compare. Okay, your y, it doesn't change, but your x changes. In short, there is a reflection along the y-axis because the y-axis didn't change. Okay, shall I say? So what will happen? Let's see the graph of it. Okay. Okay, this is the graph. Okay, this is the reflection along the y-axis. So amazing, right? Look at it. Okay, so it's perpendicular to the y-axis because, again, we the y-axis or the what I mean the y coordinates or y values haven't changed while the x coordinates or x components have changed because we multiply -1 because we are trying to get the reflection along the y-axis by multiplying -1 to your x coordinates. That's the concept behind it. So now compare the graphs, of course, as you compare it of as you can see, actually I'll highlight this one. There are image, look at this one. I'll highlight this. Okay, there are invariant points. What do you mean by invariant points? It sounds weird, right? It sounds new to you, I believe. So when we say invariant point, it is a point on the graph that remains unchanged after a transformation is applied to it. So any point on a curve that lies on the line of reflection is an invariant point. So just remember, after doing the transformation, all the transformation that you have, especially in reflection rather, then there is something point that exists where it doesn't change after several transformation that you applied in the graph. That means that point is called invariant point. So I hope we're clear about it. And I believe we're clear about it. Okay, so you don't have a choice. Okay, the transformed graphs are congruent to the graph of y is equal to f of x. Take note of that. The transformed graphs are congruent. It is still congruent because it is a reflection of the given graph. So the point on the graph of y is equal to f of x relate to the points on the graph of y is equal to -f of x by the mapping. This is the mapping now. Okay, this is along the x-axis. Okay, take note of that. Reflection along the x-axis can be represented in this mapping notation, or you can have it in this formula. Y is equal to -f of x. This represents the reflection of the graph along the x-axis. So notice that a while ago, 1, 0, it remains 1, 0. A while ago, the one that I highlighted a while ago in the previous slide, the point there is the invariant point. So you call it invariant point. So the points on the graph of y is equal to f of x, okay, relate to the points on the graph of y is equal to negative, y is equal to f of -x by the mapping. So this is the, okay, this one is the mapping notation that will represent the reflection along the y-axis. So this is the graph of y is equal to -f of x. So again, this is a transformation or a reflection along the y-axis. This is the formula of the function that can be used to get the reflection of this given function f of x if we are going to get its reflection along the y-axis. So you will just multiply -1 to your x coordinates, as I have said a while ago. So please consider that one. So the point 0, -1 is an invariant point. Why? Because after the reflections that we've done, it never changes. So that is what we call invariant point. So now I hope, and I guess we are done with this. So now let's proceed to the vertical and horizontal stretches because we don't have much time for this. So a stretch, unlike a translation or a reflection, changes the shape of the graph. However, like translations, stretches do not change the orientation of the graph. So again, stretch does not change its orientation. It will just change its shape of the graph. So take note, because you're going to stretch. What do you expect if you're going to stretch something or the graph of the function? Of course, the shape will change. Just use your head, of course. You can imagine about it. Okay, so when the output of a function y is equal to f of x is multiplied by a non-zero constant a, then the result y is equal to, okay, take note of that form. The y is equal to af of x, or y is equal to this one, y over a is equal to f of x. This is a formula for a vertical stretch. So if you have a vertical stretch, then you can use this formula. Take note of that. Okay, so I hope we're clear about it. You can take note of it so that you'll not forget it. I believe even if you are good in math, you have to remember this. Okay, this is for the vertical stretch. So there is a rule for that. This is a vertical stretch of the graph about the x-axis by a factor of the absolute value of a. Yes, and indeed. So if a is less than 0, then the graph is also reflected in the x-axis. So is it possible if it's we have a horizontal stretch? Yes, it's possible. Horizontal stretch along the y-axis. So what's the formula now? Just wait. Okay, we'll enter to the next. Oh, it's not working. Okay, this one. So yeah, it's possible that we have a horizontal stretch. A horizontal stretch can be this one. Okay, so this can be this is the formula for the horizontal stretch. So multiplied by a non-zero b, the result y is equal to f of b of x. F of bx rather is a horizontal stretch of the graph about the y-axis by a factor 1 over the absolute value of b, where your b is less than 0. Then the graph is also reflected in the y-axis. So I want you to remember that the formula for the horizontal stretch is equal to y is equal to f of bx. So what is the value of your b? Remember, your b must be 1 over the absolute value of b, where your b is less than 0. So please take note of this, because you can use this one when we try to go further in our discussion about vertical and horizontal stretch. So are you stretching your brain right now? Perhaps you did. You do rather. So stretch, a transformation in which the distance of each coordinate or y coordinate from the line of reflection is multiplied by some scale factor. So the scale factor that we have, these are the a and then the b. A for the vertical stretch and b for the horizontal stretch, as I mentioned a while ago. So please take note of that. Scale factors between 0 and 1 result in the point moving closer to the line of reflection. Scale factors greater than 1 result in the point moving farther away from the line of reflection. So it means that when your scale factor is greater than 1, or shall I say yes, greater than 1, then it will move farther away from the line of reflection. Take note of that. Once your scale factor is greater than 1, then it will move farther along or from the farther away from the line of reflection. But when it is closer to 0, it will become closer also to the line of reflection. So please take note of the behavior, because you can use that one later as we analyze the graph of the vertical and then the horizontal stretches. Okay, so I hope we are clear about it. Okay, now let's have an example. So the example is y is equal to AF. This one, remember this one? Okay, yes. That means it shows up formula of a vertical stretch. So I hope you are able to recognize this form as I mentioned in the previous slide. Okay, so now we have here y is equal to f of x. Of course, you're going to sketch and transform the graph of f of x to g of x. So describe the transformation, of course, and state any invariant points. So I was so I mentioned already the type of transformation that is being done in here. So we have here a and b. So let's now have an example. So as you can see, y is equal to f of x. Let's do the a first, where we're going to follow the 2f of x. So use the key points as I mentioned there, as projected there on the screen. f of x to create a table of values. So the image points on the graph of g of x is equal to 2f of x. This one, okay, yes. Have the same x coordinates, but different y coordinates. Multiply the y coordinates of points on the graph of y is equal to f of x by 2. Why 2? Because your a is 2. Okay, so I hope you are guided. So you can represent it in the table of values as I mentioned a while ago in a for the solution. So you just multiply 2 to your f of x because the rule in here for letter A is 2f of x. So simple as that. 4 times 2 is 8. 0 times 0, of course. 2 times 4, 2. 2 times 2 rather is 4. 0 times 2 is 0. 4 times 2 is 8. So as you can see there. Okay, so after that, you can plot the points, of course. Then compare f of x and then g of x. So plot the points in the same table of values and then you'll have it there. So now the vertical distances of the transform graph have been changed by a factor of a, correct? We multiply 2 to your y coordinates. That means we are doing such vertical stretches in here because of the factor a. Your factor a is greater than 1. Do you agree? Okay, if you beg to disagree, then you're wrong. Okay, so the points on the graph of a, y is equal to af of x are farther away. So try to compare. Compare this. Okay, compare the vertical stretch. Okay, not the horizontal. Okay, compare their distance from the along the x-axis, right? So the graph of g of x is farther away compared to the graph of y is equal to f of x. We're talking about the vertical distance in here. Okay, look at it carefully. Okay, look at this one. Oh, from here, look at. Okay, so of course it's farther away along the x-axis or along, yeah, along the x-axis as I have said. Okay. So now let's try to continue. A is equal to 2. The points in the graph of y is equal to g of x relate to the points on the graph of y is equal to f of x by the mapping xy is mapped to x to y. So this is now the formula. What I mean, this is now the mapping notation for the vertical stretch that we did a while ago. We multiplied 2 to your y. That's why you can have it x and 2y. Therefore, each point in the graph g of x is twice as far from the x-axis as the corresponding, again, twice as far from the x-axis because we multiply 2 to your y coordinates. Then the graph of g of x is equal to 2f of x is now a vertical stretch of the graph of y is equal to f of x about the x-axis by a factor of 2. Yes, exactly. It's pretty obvious, of course. And if you have seen a while ago about the graph, I couldn't see it there. Yes. Where is now the graph? Oh, the graph is gone. So the invariant points are -2 and 2, 0. If you could, if you want to go back there, -2, 0 and 2, 0. Let me see. Okay, okay. -2. Okay, this one and 2, 0. So as you can see, it didn't change. Correct? Yes, it's pretty obvious that those points who haven't changed after the transformation that we did, we call it invariant points. That's why we have -2 and -2, 0 and 2, 0 as our invariant points. Of course, if we want to look at the domain in range, of course, the domain is -6 and 6, and your range is 0, 4. Okay, where 0 and 4 are included, and -6 is -6 and 6 are included. Yeah, you can verify it. You can go back to the previous slide. Yes. So did you know that there are several ways to express the domain and range? Of course. For example, you can use words, a number line, set notation, or interval notation. So I hope we are not ignorant about this one. I believe, because I know you're all intelligent. Okay, now let's do the letter B. G of x is equal to 1/2 f of x. So now the image point on the graph of g of x is equal to 1/2 f of x. Okay, have the same x coordinates but different y coordinates. So multiply the y coordinates by 1/2. Yes, exactly. Same process as how we did it a while ago. Multiply 1/2 to your x, to your y coordinates, sorry. 4 times 1/2, that becomes 2, so on and so forth. Okay, so I believe you can follow to the process because it's just the same thing as how we did it a while ago. So plot the points after, then look at. Okay, if you compare it, of course, the vertical distances, okay, here from here down here, of course, the graph of g of x. Look at the graph of g of x. It's closer to the I'm talking about the vertical distances in here, okay? That is being transformed. The graph of y is equal to g of x. It's closer from the x-axis compared to the graph of f of x. Why? Okay, this is what I said a while ago. Because you multiplied 1/2. The scale factor now is 1/2, which is less than 1 and closer to 0. What did I say a while ago? When it's closer or when it's less than 1 or it's closer to 0, the graph is, or the graph of g of x will be closer to the line of reflection, which is the x-axis in this given. So I hope we can follow and observe. So as you can see there, your A is 1/2. So now we can have a mapping notation form as x and 1/2 y as our formula for this, or a mapping notation, because we multiplied 1/2 to your y coordinates based on the given, since A is 1/2. Therefore, class, therefore the graph of g of x is equal to 1/2 f of x is a vertical stretch of the graph of y is equal to f of x about the x-axis by a factor of 1/2. So it's pretty obvious. So you can see there the invariant points. So we have -2 and 2, or -2, 0 and 2, 0 as our invariant points, because it never changes. It didn't change after the transformation that we have done. So now the domain, of course, the domain is -6 less than or equal to x and less than or equal to 6. Or you could just write it as -6 and 6, where 6 and -6 are included. As you can see, the domain in here. So let's focus on the x-axis. Of course, for the range, it covers up from 0 to 4, because the highest point in here for f of x is 4. That's why from 0 to 4. So this is our range. So I hope we are clear about this one. Yeah, what conclusion can you make about the invariant points after vertical stretch? So invariant points will not change, of course. So that's why it could be like the x-intercepts in this case, perhaps. I guess so. So we can have the range and then the domain in here. For the range of g of x, we're talking about the g of x in here. So the domain is -6 and 6 still. So you can see. And of course, the range is from 0 to, okay, this is the highest point for the g of x. So 0 from 0 to 2. Okay, so this is the range. So I hope we're clear about it, where 0 and 2 are included. Okay, so I hope we're done. Or we're not yet done. We're still going to talk about the horizontal stretch. Oh my goodness. Okay, never mind about it. So let's do f of 2x. So same thing, but in this case, we're going to multiply 1/2. Why 1/2? Why 1/2? Remember, your b here is 2, correct? And of course, to multiply it, it must be, remember the formula for the factor, scale factor of b, it must be 1 over the absolute value of b. So if this is 2, then of course, you're going to have it 1 over 2, which gives you b, which is equal to 1/2. Okay? So this is the original form of the 2x, 1/2. That's why the factor here is 1/2. So we will multiply 1/2. Yes, we will. Sorry, I'll just erase this one. It's messing up in here. Okay, so as you can see, -2 multiply negative. Again, we are talking about multiplying your x coordinates or x components by 1/2. So from -2, it gives you from -4. Multiply it by 1/2, it gives you -2. Sorry for this line. -2, it brings you to -1, because we multiply 1/2 for 0, 0, 2 times 1/2 is 1, and then 4 times 1/2 is 2. Okay, so I hope we're clear about this one. So we have changed our x coordinates, but our y coordinates remain the same rather. So this is now the horizontal stretch along the y-axis, okay, the distance, okay, for the horizontal stretch. So now, what can you say? Of course, the g of x, since the scale factor is 1/2, it's less than 1, meaning to say it's closer to the line of reflection, which is along the y-axis. So as you can see, g of x is closer to the y-axis than the f of x, because we have 1/2 as a factor of, because the factor of g of x is 1/2, which means scale factor rather, which means the graph is farther closer, or yeah, near to your y, to the line of reflection. So again, so that's the concept behind. So your b there is 2, of course. So you can have a formula 1/2 x and y. So 1/2 multiply 1/2 to your x, as I mentioned a while ago, because the scale factor is 1/2. Remember the 1 over the absolute value of b, where your b is, of course, less than 1, less than 0 rather. Okay, so now let's try to continue and do the, of course, the invariant point. As you can see, if you're trying to, if you're going to visit it there, the graph, the invariant point is 0, 2. And of course, the domain and range is -4 and 4 and 0, 4 for the range for f of x. Okay, I'll show it again. So the domain and range, of course. Okay, this is what I said. Okay, I'll just clean it up first. Okay, so as you can see, the domain for g of x, you have -2 and -2, 0, and 2. Sorry, negative, yeah, -2, 0, and 2, 0. As you can see, for g of x, for your y, y is equal to f of x, your domain is -4 and 0 and 4, 0. And for the range, of course, you have it for g of x, you have it from 0 to 4 for the g of x. Of course, they have the same range for the y is equal to f of x, which is also 0, 4, as you can see. So the invariant point that we have is 0, 2. Okay, 0, 2. Okay, so I hope we're clear about this one. So now let's now proceed to the next. Okay, this one. What about this one? 1/2 x. Of course, your b there is 1/2. So what is the original form of that? So remember, 1 over the absolute value of b. So you can have it 1 over 1/2, which gives you 2. Correct? That's why our scale factor is 2. So now, in short, we will just multiply 2 to your x coordinate. So from -4, it gives you -8. -2 times 2 is -4. 0, of course, multiplied by 2 will give you us 0 still. 2 times 2 is 4. 4 times 2 is 8. Okay, so we'll just copy the y-axis. Okay, now we'll plot the point. So this is the point. So now let's just study the domain and range. For the g of x, of course, as you can notice, the graph of g of x is farther away from the y-axis. Why? Because our factor now is 2, which is greater than 1. Correct? So we can really compare the distances, the horizontal distances, okay? I'm talking about the horizontal distances in here because we are trying to describe your b. So the domain for your g of x, as you can see, -8, 0, and 8, 0, or you can have it -8 and 8, where negative and 8 are included. So for the domain of your f of x, you can have it negative from -2 and 2, where -2 and 2 are included. And for the range of your g of x, as you can see there, from 0 to 4, it's just the same thing as the f of x, 0 and 4, where they are included, of course. So now, yes, as I mentioned a while ago, you can just have this one. Xy is equal to 2xy. That means your 2x, we can have it as a mapping notation because we just multiplied 2 to your x coordinates or x components based on the given scale factor that we have. Okay, so I guess we're done in here. So always remember that more transformations, so reflections in the y-axis will do this one or this way. Reflecting the x-axis changes the sign of y. Okay, remember that one. So y is equal to f of x becomes negative f of x. So reflecting in the y-axis changes the sign of x. So y is equal to f of x becomes y is equal to f of negative x. So the examples that follow illustrate combinations of the transformations, translations, stretches, and reflections. So I hope we're clear about this one. So this is a drill. So I want you to do this one. So if you have some questions, you can just ask and PM me personally. Okay, we call it a day. That's all perhaps. Okay, so we're done with that. So I hope you have learned something, but if you cannot really get it, then you can just PM me personally. So that's it. Have a great day.